Hey guys, in this video I'm going to go over an example of doing Gibbs sampling, which is a type of Monte Carlo method, and I'm going to do Gibbs sampling with data augmentation. The example I'm going to do in the video is based on an estimation problem that I'm going to try to solve using Monte Carlo methods. I actually talked about the same problem in the last video I did because this is like a project I was working on, so I will link in the description box below the video if you want more background information on this problem, but I think you can just watch this video and understand the main idea of the problem without watching the other video. So basically, the example I'm applying Gibbs sampling methods to is a blood typing problem. So we have sample data from a population of people's blood type, and you have 1 out of 4 possible blood types that you can be. You can have blood type A, B, AB, or O, and these are the sample data below, and that has a probability as displayed in this column here, and your observed blood type depends on one of 6 genotypes. So you can have genotype AA, which would give you blood type A, but AO would also give you blood type A as well. So that distribution of your genotype, underlying genotype, also has a multinomial distribution with the following underlying probabilities. So we usually do not observe genotype, we usually just observe your phenotype when we do blood testing. We observe this, and we kind of want to estimate the probability of having a certain genotype. And what we want to estimate in particular is the frequency, the genetic frequency of the different alleles, so the A, O, and B. So the problem is we have this sample data, and we want to estimate PA, so let's say the proportion of A, the proportion of B, and the proportion of O. So that's the main idea with the problem. And in this video, we're going to use Gibbs sampling with data augmentation to solve this. So I'm going to, in this video, estimate these parameters using Gibbs sampling to estimate from a posterior distribution. So this idea comes from Bayesian statistics. So this is also kind of like a Bayesian statistics video. And the idea for doing this type of analysis comes from this paper, The Calculation of the Posterior Distributions by Data Augmentation by Tanner and Wong. So I will also put a link in the description box below for this paper. And anyway, let's go ahead and get started with the video. This is going to be kind of like a demonstration more than an in-depth tutorial. I'm kind of assuming you know some background information on all of this. Otherwise, the video would be like 10 hours long. So we want to estimate PA, PB, and PO, where the sum of the alleles has to equal 1. So PA plus PB plus PO has to equal 1. And I said we're basically going to use Bayesian statistics to estimate those 3 parameters. So we need to calculate or sample from the posterior distribution. For now, let's assume that we could observe the genetic data, which we don't observe. We observe the phenotypic data. But we're going to get to that in a minute. But let's say we know the underlying genotypes of our samples. Then a posterior distribution could be defined as follows. I'm going to say P of PA, PB, PO, given the genetic data, is proportional to the probability of your genetic data given the parameters PA, PB, PO times a prior distribution on the parameters. In Bayesian statistics, this is one way that you would define the posterior distribution. So it's a distribution of the parameters given your data, and that's proportional to a likelihood, which is the probability of your data given your parameters, times a prior distribution on the parameters. So we would say the posterior is proportional to a likelihood times a prior. The problem with this example is that we do not actually observe the genetic information. Instead of observing the genetic data, we observe phenotypic data. So instead of calling this X, I'm going to call this Y because we observe 1 of 4 possibilities instead of 1 of 6 possibilities from the genetic data. So we cannot actually sample from the posterior distribution yet. So instead of observing X, we observe Y, which I'm going to define as Y1, Y2, Y3, Y4, and these are the observed sample data of the phenotypes. So I'm going to say Y1 is 89, Y2 is 642, Y3 is 195, and Y4 is 657. If we considered only the phenotypic data that has 4 possible outcomes, and we tried to draw from a posterior distribution given y instead of given x, we would not have a complete likelihood. So we'd have a problem here because we would not be able to get a conjugate prior to the posterior distribution. So we would not be able to assign a conjugate prior, and that would kind of complicate our ability to estimate PA, PB, and PO. Because we prefer having a complete likelihood to be able to get a conjugate prior for the distribution, this is where data augmentation is going to help us. Data augmentation, as the name implies, basically means we're going to try to add to our sample data that we have. So we're going to try to augment it to be able to form a complete likelihood. So if we go back to the data that we do observe AB, we do observe O. But for A, we don't know if someone is AA or AO, and for B, we don't know if someone is BB or BO. So in that case, we have like 2 missing variables. And so with data augmentation, what you do is you create latent variables for your missing data, quote unquote missing data. So I'm going to define Z1 as my first latent variable, and I'm going to estimate that, and that's going to be an estimate of the number of people who have AA genotype. And I'm going to do the same thing for the observed phenotype B. So I'm going to say Z2 is going to be an estimate of the people who are BB. Using these latent variables and estimating these values, I can then plug it in to my posterior distribution and basically augment the posterior distribution, augment the likelihood, and then I will be able to form a conjugate prior. So if we have the probability of PA, PB, PO given Y and given Z, then that will be proportional to the likelihood of Y and Z given the parameters times A prior. Instead of trying to write all that out, I just pasted it here. And so I defined theta as a vector of my parameters. So PB, PA, and PO are in the vector theta. So we have the posterior distribution of our parameters given observed phenotypes plus the latent variables is proportional to the likelihood, which is now a complete likelihood, times some prior distribution on the parameters. And then we can do multiplication and simplification to basically get that we have that the posterior distribution is proportional to PA to M1, PB to M2, PO to M3, where M1, M2, and M3 are defined as follows. So that's a mix of the sample data and the latent variables, which we have to estimate. And now, because we have a complete likelihood, we can form a conjugate prior to this distribution. So this is a complete likelihood for the multinomial distribution for the genetic data using the latent variables. And from that, we can assume, or we can place a conjugate prior on P of theta. So we're assuming the prior is going to be Dirichlet distributed because that's the conjugate prior for a multinomial distribution. So I'm going to place a Dirichlet prior on the parameters. So that means that the probability of PA, PB, PO is going to be proportional to PA to the alpha 1 minus 1, PB to the alpha 2 minus 1, and PO to the alpha 3 minus 1, where alpha 1, alpha 2, and alpha 3 are Dirichlet parameters. And in Bayesian statistics, because this is a prior distribution, you would call these 3 parameters hyperparameters. By substituting this prior distribution back into the equation for the posterior distribution, you would then get that the posterior distribution, and this makes sense because it's a conjugate prior, the posterior distribution would also be distributed as a Dirichlet distribution. So now we're going to have that the probability of theta given yz is Dirichlet distributed with parameters m1 plus alpha 1, m2 plus alpha 2, and m3 plus alpha 3. In Bayesian statistics, when you don't know anything about alpha 1, alpha 2, and alpha 3, which are the hyperparameters, you can use what's called a non-informative or flat prior. So for the Dirichlet distribution, the non-informative prior would just be setting alpha 1, alpha 2, and alpha 3 equal to 1. So I'm going to use that in this problem. So I'm going to assume I don't know anything about the prior distribution. So I'm going to set that to 1. So our posterior distribution is going to be distributed Dirichlet with M1 plus 1, M2 plus 1, and M3 plus 1. Then, now that we have defined the posterior distribution, we can actually sample from this using Gibbs sampling. So this is actually the first part where Monte Carlo sampling is going to take place. We have to use Gibbs sampling because we don't actually know the true value of the latent variables. So we have to estimate those. In Gibbs sampling, you can estimate those by sampling from a conditional distribution. So basically the way Gibbs sampling works is it's an iterative Monte Carlo method, and at each iteration, we're going to sample from a conditional distribution. So we're going to condition on the parameters to estimate Z1. Then using a different conditional distribution, we're going to estimate Z2. We're going to use those estimates to sample from the posterior distribution. Then by sampling from the posterior distribution, it's going to update the values that you would use to sample from the conditional distributions for Z1 and Z2. And basically you just iteratively update these values until they converge to your final estimates. And then you don't really need the estimates for Z1 and Z2 anymore. You just use the final estimates of your posterior distribution for whatever you want. So in this case, we want to estimate the 3 parameter values in the posterior distribution. So I have some R code that I'm going to show from when I did that, but to show you what the distributions that I'm sampling are, they're going to be Z1 conditional on Y, and then the parameters PA, PB, PO. That conditional distribution is going to be binomial, and it's going to be binomial y2, and then PA squared over PA squared plus 2PA PO. I'm not going to show how that was derived, but you can derive that just using math. And then the second conditional distribution is going to be y given the parameters. And that second conditional distribution is also going to be distributed binomial with parameters y3 and then PB squared over PB squared plus 2 PB PO. So then when we actually run the Gibbs sampler at each iteration, we're estimating a value of Z1, we're estimating a value of Z2, then we're estimating the PA, PB, and PO values. So we sample from the conditional, sample from a conditional, then sample from the posterior distribution. At the next iteration, we plug back in the estimates of PA, PB, PO into the parameters of the conditional, and then the posterior distribution also uses these estimates. So each iteration has to update all the values, and then you do that until the sampler converges. In the last part of the video, let me actually go over the Gibbs sampling code that I have, and I will put a link in the description box below for this code, but let's just go over it briefly in the video as well. Because we need the Dirichlet distribution to sample our posterior distribution, I defined a function that would do that sampling. I think probably R does have packages or does have an ability to sample from the Dirichlet distribution, but I couldn't find a function that worked exactly how I wanted it to. So since the Dirichlet is related to the gamma distribution, you can actually just define it manually, and this worked for me. So this is a Dirichlet with 3 parameters, A, B, C, that you plug in. Then for the next step, I had to predefine some vectors and matrices for doing the Monte Carlo sampling. So I kind of just randomly picked that I was going to do 2,250 iterations of the Monte Carlo sampling because we have to estimate the latent variables and then the 3 parameters. I initialized an empty vector for Z1 for all the iterations, for Z2 for all the iterations. So these are just 2 0 vectors. And then I created a 0 matrix with all the iterations and 3 columns for the 3 parameter values I'm trying to estimate, PA, PB, and PO. I have my starter values, which are the sample data. With Monte Carlo sampling, you always have to start with certain initial values. So for Z1, I just set the initial value to 500, same thing for Z2. And for my parameter estimates, I set the initial values to 1/3 for each value. And the hyperparameters I'm using are 1. So alpha 1 is equal to 1, alpha 2 is equal to 1, and alpha 3 is equal to 1 as well. So then the next line of code actually runs the Gibbs sampler. for the 2,250 iterations. So I conditionally estimate from the binomial distribution for Z1. I estimate the conditional binomial distribution for Z2. Then I plug those values into the parameters M1, M2, and M3, and then plug those values into the posterior distribution at each iteration. So each iteration is going to update the values of Z1, Z2, and PA, PB, and PO. In Bayesian statistics, once you have sampled from the posterior distribution, one thing you can do is get the posterior means. And so that could be one possible way of estimating the parameter values. You can also look into estimating the mode. That's sometimes used in Bayesian statistics. But in my particular case, I estimated the values using posterior means. So then that just means I had to find the mean of the sample values from the Monte Carlo sample. You usually do burn-in with Monte Carlo methods, so I just threw away the first half of the samples and I took all the values of the second half. So I took basically 1,125 values in the second half of the vectors or matrices. So that gives me the estimates 0.266, that's one parameter value, 0.094 as a second parameter estimate, and 0.64 for another parameter estimate. And just to show that the values did converge at the end, I plotted the density plots just to show that the density plots pretty much show that there is one unimodal mean for the distributions. So for this problem, after doing all that work, we have that PO hat is equal to 0.640, PA hat was equal to 0.266, and PB hat was equal to 0.094. If you watched my previous video, the true values are 0.638, 0.268, and 0.095. So this gives me values that are very close and tells me that the Gibbs sampling method worked. And these are the estimates for the underlying genetic frequencies from the population. And that's it for this video, and thank you guys for watching.